Okay, in this section, I'm going to talk about how we can compute uh, the contingency coefficients. And I am adapting this from the 111 um, lectures or start 111, that's level 100. So if you remember, you did contingency coefficients, and some of these contingency coefficients, so you must revise this so that you'll be in a position to now use R to do this in R 240. So just a quick review that the contingency coefficient is what a measure of the extent of association or dependence between or two categorical variables. Remember, in the last class we did talk about correlation, right? Which is between two quantitative variables. Okay. So here you have the phi contingency coefficient, Cream V, there's kappa contingency coefficient, Chopros, Pearson's, and a host of others. Okay, all right. Now, so basically, the phi contingency is computed from a chi-square value, and because you have this slides, I'll hope that you go back and read on it. But essentially, what I'm going to do here is to just show you the formula, and then we will implement this in R. So the phi contingency coefficient is defined as this. So it's just what the square root of the chi-square divided by the sample size or the total number of observations. Okay, and how do you calculate your chi-squared? It's just what the the difference in the observed minus the expected, and then you divide by the observed value, right? And so if you have the other ways of computing it, but basically I'll use the one up there, which is the square root of the chi-square statistic. The interpretations, we know how that is done, so I'll send you either this or another table for the interpretation. Here, so this is an example, and this example, I will use this in R, okay? So basically you have um, um, the variable residential status, and then uh, the students, whether the student is what a fresh student or a continuing student. So you are studying two variables, that is the residential status and let's say the status of a student, whether you're a fresh or a continuing student. So in if I want to do this, remember this is what in a matrix, right? Okay, so in R, I need these two, or not all of them, but these four values to be entered, and it must be done in either as a matrix or I can table them as well if I have the raw data. Remember, the raw data in this sense will be that you ask two questions. What is your residential status? So the residential status, the person will either say um, a resident student or a non-resident, right? So you have two questions. So I can get this in like a matrix with what, two columns where each row is just like we did in class. Each row is what an individual. So an individual, we ask you of your residential status and your status, either you are a continuing student or a fresh student. So this will be either yes, the other no, or yes, or and so forth. So once you get I'll show you how to do each of these right in R. So this one, because we have already tabled it, I can just enter it as a matrix, okay, and then I compute my chi-square value. I know the n, so I divide by n, and then I get my results. Is that okay? So that's the other way. The other way round, I will have two variables. So I have resident and non-residential, and then I table them. So that will count the number of times each of them falls within each category, and then you get your chi-square value. Now, so I go back or I go on to the other one. You can go through this to um, but I will essentially calculate this with R. And now I'm going to the other section, which is on Kramer's V. Remember Kramer's V, if I may add, the phi contingency coefficient is for only two, it's only when you have what, 2 by 2 contingency table, like the one I did, you have resident, 2 columns, 2 rows, if I should put it that way. Now, when you have more than that, that phi contingency coefficient is not appropriate. So one of the other contingency coefficient you can use is what the Kramer's V contingency coefficient. And that is essentially computed using the same chi-square value, or you take the phi squared or the phi value, you square it and you divide by t. And t is what? The number of observations, or um, total number of observations, that's k minus 1. Okay, so t is just the number, n, as we know, is the total number of observation. T is just the minimum of the row and the column. Okay, so once you get the minimum of the row and the column, you subtract by 1, and that's our value for t. So these are the two statistics I'm going to do. The others, you can read through it, but we can implement that in R as well. So I'll give you, I'll tell you a package that you can get all the other ones and so forth. But I'll do these two from first principle, so that you'll be in a position to continue with the others. Okay, so now we come to R, and we are going to deal with writing functions and in this case, we are going to write a function for computing measures of association for categorical variable. So from this, you should be in a position to do what I asked you to do in class. So for this function, it must take in a matrix. So before as I said, so we want to take a matrix, then we compute the phi value, and then also we compute the Kramer's V, and then we can do what? Return the Kramer's V and what? The phi contingency coefficient. The others, I will let you try them on your own, and I'll give you some packages you can get this from quite easily, rather than writing your function to compute them. But it is important that at this stage we can even construct a function that will compute a chi-square value. That means it takes each or observe, you compute the expected, you subtract, you square, and you divide by the expected, and you sum all of them to get your chi-square value. Now, yeah, so what do we do? Okay, now let me say, if I go back to the example, I want us to calculate the example from your what you did in level 100. So the values are, I would say, 21,630. Let me try and copy this to R straight away. Oh, what is happening? Okay, so like this, just to guide me so that I don't have to come here again. Okay, so what do I need? Let me comment this out. So I comment this, that, and that, and that one. Okay. So if I want to construct this, I'll say, let's say math, and it is a matrix. It takes in the values, and this I'm going to take them row 6. So I'm entering them row wise 30 and then 13. That's all I need, right? And the number of rows, I need 2. The number of columns is 2, but as I said, I may not necessarily put in the column because I can compute it by itself once I know the sample size and the number of observations and yeah. But the key thing is by row. So if you look at this, so by row be equal to false or true. Remember when I was writing this, I did it by rows, not the columns. If it was the columns, I was going to enter 21 and then 30, and then I'll write 66 and then 13. So this one we should say by row is equal to true. This is important. Other than that, you get a matrix that is different from what you set out to achieve. So there it is. 21 to 20. So, okay. So now I'm in a position to write my function. Okay, but before I do this, I want to go to check what chi-square. There's a function called chi-square test. Other than that, I have to write my own function to compute the chi-square value, but I want to call in an inbuilt function to do it for me. Okay, so the chi-square is that you can have a table which has um, and you pass your matrix to it and the observed, expected. So we can use this to get the observed, the expected, the residuals, and so forth. Okay. But here, what I want is a statistic. If you go, okay, they don't have, the statistics, the value of the chi-square test statistics. So that is what I'm interested in to do my work. But as I said, if you want the observed, expected, and you want to subtract and square and divide by the expected, you can do so from the chi-square test as well, or you write your own function to compute those things. Okay. And now, so with that, I think I have enough information now to construct my chi, the phi, and then what the Kramer's V. So what do I do? Maybe I should construct one function for each of them, and then I'll call all the two functions to compute them, and then I return them. So that's one way of doing it. So I will say phi, so I can say phi dot fun, phi dot fun. So this function takes in, let me say, a matrix. So I say a matrix. Remember, matrix with small m is what? It's a keyword, so we don't have to use it. Okay. So before this, I can put a comment that a function computes what? A phi contingency coefficient, right? Okay. And our function takes in a matrix and computes a phi contingency coefficient. So once I have my matrix, what I need is that I need the chi dot value. Okay. So let me say chi value. The chi value is just, now I'll say chi square first. Then I input in my matrix. Okay, and then I I write statistic. Remember that you see the chi-square is the output will be a list. So if I want the statistic that I'm interested in, I must do I must do it like that. So statistic, remember the values, you say value. So what it means is that if you run this function, the results, you get results, a list with class HS containing the following elements. So because I'm interested in just a statistic, I have to now copy this and paste. If I want to do this, I can do good. You copy and paste so that you don't make any um, mistake. So that should give me an idea. And sorry, I remember that this. Let me just track back and name my columns. Is not very necessary, but of course it's good so that when we display our value, we have the. So what was the column names were? If I go back, uh, so residential, non-residential, and the fresh students and continuing students for the rows. So sorry to residential, residential, and then non-residential, non-residential, and um, the core names, sorry, the row names should be row, row names should be fresh student and then continuing student, continue, continue, continuing student. Okay, so I can do that. Okay. Now, I I wanted to check this before I even go to the function. That should have been the first thing. So I track back. I check chi-square for my matrix so that I can use that to explain what I was talking about here, which is the value. So if I do this, remember this is what you get. So it's a chi-square test statistics with Yard's continuing correction, and this is a chi-square value. If I had um, like made this or named it and then I go to summary, maybe I should do that and say chi. Um, so let's say chi t, chi, chi t. And so if I assign this and I say maybe summary of chi t, um, you see, so there it is. So all the things that were listed as summary, you have all of them. So parameter, statistic, parameter, p-value, method, data name. Remember the p-value with those doing start 223 will know about this. So observe, expected, received, or and so forth. So if you want any of these, you can get it quite easily. Okay. So if I want the p-value, for example, I will say chi t, and then I put the dollar sign there. All of them, because it's a list, all of them, remember our discussion on list, all of them will appear. And then if I turn to p-value, it computes it for me. So in the same way, because I am interested in statistics, I can say, sorry, statistic, and then it computes this. So um, my chi-square statistic is what is 0.203. If I'm interested in, sorry, the observed,
Remember the observed. The observed is what we imputed in, okay? And the expected, if I'm interested in the expected, I squared t, I'll go to what? Expected. So the expected frequency is that one. And remember the chi-square value, we will take 21, subtract 19.67 from it, divide by 19.67, and then go to 6 divided minus d squared and so forth. So that's how this is. So I think we are in a position now to write our function. So we just take our statistic, okay, and yeah, we take our statistic and then, okay, so once we know our statistic, the next thing we do is that we compute our our phi value. And remember our phi value was what? It's the square root, right, of the chi value or the chi-square statistic, okay, chi-square statistics. And then we divide by what? The total number of what? People. And the total number of people here, we can find it as what? The sum of what? Matrix. So this one, the sum will sum everything in the matrix, right? And then we get that. So this is the chi-square value. And then we return our chi-square value. So our phi value, so not chi. So there it is. So this function is enough. So I want to now run this and check if it is okay. I'll input in our matrix. Okay. So there was no red or warnings or anything. So there's no error. So so calling the phi function phi.fun to compute the phi coefficient, contingency coefficient, coefficient. Okay. Now, how do I do this? It's simple. You call the name. Okay. Remember, we have already done our math, right? Our math is a matrix. I can display this, right? Which is what you have in your 111 notes. Okay. So I just input in this math. So this, and then my matrix is equal to math, equal to math, right? And then I compute it. So the and um, so this is not a chi-square value, but the phi. And I'll tell you why this is so. You see, when we compute the chi-square value, it, it comes with a name. The chi-square statistics, see, is a chi-square. Now, for us to be able to omit the name, otherwise it will carry on with all our calculations. So although we've computed phi, it is telling us that it's about chi-square. So for me to be able to, I can take the name out, okay, and to take the name out, I can just say as the numeric. So it's just a numeric value without any name. So if I do this, it will take off the name, and I don't have any name like chi-square. So instead of I'll go back to my function, and then here I will um, I will put all this under out in a numeric form, and then that should take away the the name. So that's one way of doing it. There may be other ways you can try to unname such a value. So for it to take effect, I must go back and rerun this function. So I copy all, there's no error. So now let me do so it computes it. Okay. Now, one more thing. This function just computes a value. And maybe I want to show it to an audience. So what I can do is to write something about it, right? I write a test so that it comes with it. So one way to do so is like a cut. You can do a cut statement. Okay. So cut, and then I say, so cut, let's say the phi square, the um the phi contingency coefficient is given by something like, or I can use paste as well. So let's try this. I can also use a list. So there are several ways you can do this. Okay. So this one, at least it gives some information about what is being displayed. Okay, so you can use a cut to do so. Another way is to use paste. So paste, or alternatively, you can use a list and say the chi-square contingency coefficient or the phi contingency coefficient is given by so and so. So there are various ways you can use in getting information. So this is for the phi, okay? And I can do another one that will call do the Kramer's V, and then I call it maybe Kramer V. So this function, so at least this we know most of the things. So it will also take a matrix. Okay, I can go and copy whatever I have over here and come, and then I will modify it to take care of the Kramer's V, right? Okay, so remember the Kramer's V um, will need a chi-square value, okay, and remember our T, and remember T is what for transpose, so we can't use T to small letter T is for transpose, okay, so we cannot use T in our formula as we had over there. And also, if we want to use capital T is also for true, so we can't use it. So we must find a way, and we can say, let's say T dot K, something like that. And T dot K will be, so it's the minimum value, okay, of, right, a function which is n row. Remember, n row will give me n row of matrix. So it's what? The T is the minimum of n row of the matrix or n core, okay? It should take the minimum value, n row of matrix n, or the core, right? The minimum of this, and then I subtract 1 from it. Is that okay? Remember what we did. I can go back to the formula and check for you. The Kramer's V. Okay, so there it is. It's what? K is equal to minimum row column. So I say min, and I put this as what? A vector. So that's why I use C, then n row, n core, and then it takes it. Then I subtract 1 from it, I get a T. So that's it. Okay. Now, the next thing is that I must compute my Kramer value. So the Kramer value here will be also square root, okay, in this case, phi, sorry, I don't need phi, so let me just, we can use a phi, but let's just comment it out so that we use our, what we want to do, okay? So I need this square root, okay, so I can copy this and modify it, right, easy. So square root Kramer value divided by what? This one is a sum times. So I put that in brackets, sum times or times t, times t, tk, t dot k, right? So that's our value, okay? And then here, so here we will write the Kramer's V, Kramer's V contingency coefficient is given by, and it's not this, but Kramer value, so Kramer value 5. All right. So we are in a position now to compute, um, to use our function there. So I don't have any distance. So I can copy this and change to Kramer's V, and say Kramer's V. Right. So contingency coefficient. So I need this function in there. Yeah. So 0. Remember, all these have so many decimal places. So maybe we can go in and even tell it to use what? Maybe 3 decimal places. So 3 decimal places, I'll go to round. Okay, I'll use round. Remember from your round and Kramer's value, and I say 3, right? So round, dig it, equal to 3, and then remember to close this. So I think that is enough. Okay, so I'll do this and then check. It works. So it turns into 3 decimal places. So I can go to this place too and also input in round. And then I say how many decimal places? 3. And I close the bracket. Now, so let me do this. Okay. So that's also the same. Now, why are they the same? They are the same if you go to here. Remember from your 111, they will be the same because they are all 2. It's just 2 by 2 contingency table. But if I were to use more than 2, of course, I know the 5 function is not working. It doesn't work. So remember here, I can write a function to now combine the 2. Okay, so it's up to you if we ask you to do this. And see, I am because I want to call these functions within the function, I can put the name in quotation marks like this. But if I do so, I must run it. So if I do it this way, I'm in a position to call them within another function. So I can create another function, call maybe combine function. And this, you see, I could have just computed them individually. Or alternative way is to call the functions I've already done. And that is what I was asking that you do in the correlation. Remember the correlation, although you are using one um, uh, function, either the call or call.test, you have to specify the method. Okay, the method you are using is either the Pearson's, the Spearman, and the Kendall. So if I ask you to do this, it means you must have 3 calls. Each of them should, the first one may take Pearson, the second one Spearman, the third one Kendall. So you have 3 different outputs to put together. So either you call them on its own, or you you do it. Okay, so I combine this by, let me say combined, and that's going to be a function, a function, a function. The function takes in matrix. Okay, when it takes in matrix, it must compute phi, let's say value. Phi is what? Then I call my phi function, phi.find. Okay, phi.find. So this is quite simple because I have already done those two functions. So that's how you can call in um, lemma because it's name V, I can use. So um, I can call Kramer's V matrix is equal to matrix. So in this case, matrix is equal to matrix, and the same for here. So once I compute those two, I can name them, okay? So I can say output, let's say output is or C, and then I call this, and then that, oh, and then this one. So, and this is a vector, so I can say names. So names, and then I give it the values. So not values, but the names. So the first one, sorry, the first one is of phi contingency, contingency value, and then the other one is of Kramer's view, Kramer's, Kramer's view. So Kramer's view, they are all contingency anyway, but I don't want to have so many names, so I just shorten it, and then I need a return output. And also put this in this. So let me, so instead of writing now, what did I do? I want to just name them, right? Just name them. So now let me call combine and give it the mate, the matrix is equal to math that we've done in C. There. Oh, okay. So each of them actually gives, yeah, so this will be a problem. It's because I was naming the other one, that cat. So you see, each time it calls, it writes the phi contingency coefficient is given by the Kremers. So it is writing those cat statements I use. So if I want to avoid this, I can also go back to those functions and take out the cat, comment it out. Okay, so I comment those cat statements out, and then I won't have that problem. It's up to you actually what you want to do. So in now there are so many. There's no one way of doing things. There are so many ways you can use. It's up to you to explore. Okay, so but everything I do within that function, I must rerun it for it to take effect. Okay, so now if you look at this, I can now combine my statement and there it is. So you see now it doesn't um, write those statements over here. So that's how you can write functions on your own to do certain things, and that's what I was requiring of you in um, the other work I required you to do, so that you'll be able to call different functions or work. I can also do the same thing. You see, the combine function, I may also just copy what is I did for the phi and what I did for the Kramer's V and put it here instead of calling the functions to do so. So it's basically up to you. And so, but basically, that's how functions can be written. And I hope you go through some of these things so that I can take another example. Okay, so let's say an example. Let me look at a data set, for example, wall breaks and wall breaks. Let's see. So wall breaks is a function like this. So look at this. Okay, so this is it's not a function, but it's a data set. Let's see where I think it's in data set. So wall breaks. Um, So warp breaks. Okay. So this data set gives the number of warp breaks per loom, where a loom corresponds to phase length of a yarn. Okay. So it is a data frame with 54 observations on 3 variables. Okay. So, but what I want to do, because the 3 variables use, look, 2 and 3 are factors, right? A or B. This one is 3 levels. So what do? I, I, if I want to get it in a matrix form, you see, this one is not in a matrix form. I want to, for example, use a wool and tension. So, because so I can use what is called with statement. So with takes a data and then an expression, what you want to do. So what I want to do is to convert the tension and the wool, okay, into a table. So I'll say with wall breaks, okay, table. So then the function to create the tabular form is called table. Okay, so I copy wool and then tension. Okay, wool and then tension. So you see this one, I'm creating the matrix from an already data. So let me tell you what you see. So this is what I have. I have tension as the names of the columns, which is um, L, M, or H, and then on the rows I have what? The type of wool, which is A or B. Remember, this is the 2 by 3 contingency table. So if I want to study the relationship between these two tables, right, it is not it is, sorry, the phi is not an appropriate um, um, contingency coefficient to use. But for the purpose of this example, I compute the phi as well. So in an examination, if I've given you a table, if I tell you to study the relationship between 2 variables and one of them have one or more categories, you don't use the phi. If you use it, it means you don't know what you are doing. So in order to do this, I will say, I can say this data is called warp, warp, okay, and then I do this, okay. So now I can get my combined function, okay. I can now take my combined function with warp, and the matrix is now warp, all right? Okay, and then I do this. Remember, each of them is what? 0, 0, 0, 0. And if you remember, this one is like they are all equal, 9, 9, 9, 9, 9, 9. So basically, there's no association between them. Okay, and so forth. So I will send you a document that will help you to understand the how to use some packages and so forth. So I'll send you this, and then you can go through some of them, including how to interpret some of this. So, for example, when you have small, the Kramer's V, and so forth, how do you interpret them? Okay. So, very small association between them, either is medium or large, and so forth. So, I'll send you this, and then that will help you with the interpretations as well. All right, so I think that will be the um, end of my discussion here. Let me check if I can get one more example where you have some kind of, uh, so you can go to package data sets and check through so that you can have a data package. So I can say data set. So that's package data sets. So there are so many um, state.x77 and cars. Okay, yeah, let's look at cars 93. Yeah, let's look at cars 93. Yeah, so cars 93 have some categories. So the type of car, and let's say the type of car is a factor, and then airbags. Okay, so let's tabulate airbags and what type of car. Okay, so there we can say car dot. So the car data we will say with cars 93 we want to table and then I call for the type. So we want to study the relationship between the type of car and the um, okay, so there are several levels. What did I just say? Airbags. Okay, the type of cars and then airbags. We are studying two variables, airbags. So airbags is a factor, none. Drive only, drivers and passengers. So let's see what happens. Car dot that and see. We have this contingency coefficient on what? Airbags and then the type of car. Okay, so now we want to use our combined um, metric. So remember that in this case as well, it is only the Kramer's V that is valid. Okay, only Kramer's V that is valid. Because this is not a 2 by 2 contingency table. So yeah, and remember this is also a problem. So this is of course we are not looking at this because it's not, but the Kramer's V is 0.42, right? And 0.42, if you check, that is moderate, right? Or if you come here and your K, the minimum is around 4. So it is still large. Okay, so this is a large association between so yeah. So yeah, I'll send you a site where you can read about what you are doing as well, and so forth. So I'll paste it there, and then you can go there and look at it. But I want to comment on this, which is also good as you move on, you do this later on. But you see, in the chi-square, it always telling you that chi-square approximation may be incorrect. Why is it incorrect? Look at it. In some cases, we have zero observation. When you are using a chi-square statistic, it is assumed that each cell contains at least 5 observations. Other than that, it's not a good approximation. Now, there are other ways we can use a Fisher's exact test and so forth, but I'm not going to go there. But just so you know that when you are talking about contingency table, you must be mindful of these things. And I'll promise you about it, and which you can do later on. So that's how this session will be about it. And now I think you should be in a position to do that of the correlation, do all your three and comment on it as I talked about. Thank you.